Okay, so picking up where we left off. After a suspicious return address has been found in our kernel system thread, we go down to here. I already know this is an array which tracks suspicious threads by the element being thread ID, the first element being thread ID, and the second element being the return address. How I know is because I already reversed it, right? And you can usually tell because I did this is stupid shit where it does -1 accessing an array. Don't know why it does that, but anyways. We go down, we do a do loop where our thread ID is equal to the first element in our array. If not thread ID, meaning our suspicious thread array is empty, or the current thread ID we're tracking is equal to thread ID, so, oh, and return address is equal to gsusthread. So if this suspicious thread is already tracked, we break. Um, if it's not already tracked, we increment our table index. Um, Obviously, if there is nothing in there, we break too. But if there is something in there, and this is the second one we're logging, for example, the second suspicious thread we're logging, we increment our table index, we increment our gsus thread, while our table index is less than 10. So Battleye tracks in their driver at most 10 suspicious threads, or specifically 10 suspicious system threads, right? Anyways, we go down, we set table index underscore whatever, it's a copy of table index. We check if table index is less than 10, so if we have space to track more, and if keyword, this one, 2 times table index does not exist. So if the table index we're looking at right now is empty, right? Yeah. Or v4, this causes a forced scan. I'm pretty sure. I'm not sure why this would be set. Anyways, we go down, we allocate a pool. Um, then I already reversed this function. It's virtualized, but I set a breakpoint and I followed it. This basically just copies 40 bytes from the suspicious return address. So if we found a suspicious return address, we go there, we copy 40 bytes. If that works, so if it's greater than or equal to 0, we go down, we do a while loop. Ignore these names, I already renamed these because I reversed it again. Anyways, we go down, we do a while loop where we check for jump instructions, right? We keep incrementing by byte index, we keep incrementing by 1 until we encounter a jump instruction. If we don't, we go to label 59 and we generate a basic report. Let's assume that we encounter a jump instruction, right? We go down, um, we get the relative address, um, we do jump offset plus that relative address, so we get the actual jump target. So the exact memory address that jump instruction is targeting. We check if that address will not cause a page fault when we access it, so MM is address valid, just for safety reasons. If that fails, or if we cannot copy 40 bytes from that second or from that target jump address, we break. Let's assume we copy 40 bytes, so now we went from the return address, we copied 40 bytes from that, we found the jump instruction, and now we are analyzing the memory that the jump address is targeting, right? So it seems their stack walking really focuses on jump instructions. That's what they care about a lot. Anyways, we check if hop count is less than 10. If it is, it seems this is some sort of array which gets set to our jump target, which with a storage of 10 max. So I'm guessing this is for the report. If we if our hop count is less than 10, we access this array and we set it to jump target. So basically, to keep track of the frame chain, I guess, if that makes sense. We also have this 5 hops variable. I know it's 5 hops because if hop count is 5, 5 hops is 1. So just another thing to include in the report, which I mean, it's a pretty big indication of manually loaded code or something suspicious because there's no reason for a regular system thread to go through jump x into jump uh, y, etc. Like 5 different jumps into different parts of memory from one system thread that doesn't belong to any valid module. Anyways, we're still in the second one, by the way, or we are in the target of the first jump instruction. Now we look for another jump instruction. So from jump x, now we're in x's memory address. Now we're checking for jumps there. If we don't find one, we go to label 44. Let's assume we find one. If we find another jump instruction, we do jump target plus or equals this. Um, and we do this until we don't find a valid jump instruction, or our hop count is less than 100. So Battleye will walk 100 different jump instructions until it doesn't find anything else. Or sorry, until either it doesn't find anything or until it reaches 100. But it doesn't keep track of all 100 jump frames, jump instructions, sorry, jump addresses. What the fuck am I talking about? It only logs 10. However, it will in the report it will keep count of hop count being 100, which is very weird, right? Not the report. I'm saying if your code does that, it's weird. Anyways, it will do this in a loop, and it will generate a report specifically with the 10 first jumps, 5 hops, and the number of hops that it went through. And that's all included in the report, I believe, which I will cover in the next video. Yeah, that's it, I guess.